Welcome to this video on conducting a two-sample hypothesis test with a dependent mean. Let's begin. After watching this video, you should be able to conduct a two-sample hypothesis test for two dependent means. Let's review the steps in a hypothesis test. First, we must determine whether the requirements for the hypothesis test are satisfied. Then we will state the null and alternative hypotheses. Then we use either the p-value or the critical value method to test the hypotheses, make a decision to reject or retain the null, and finally we write a statement to summarize our findings. Example, fuel efficiency. An automobile repair shop claims that it can increase the fuel efficiency by giving your automobile a tune-up. The highway miles per gallon fuel usage on 30 randomly selected vehicles was measured before and after the tune-up. Is there sufficient evidence at the 5% significance level to suggest that the tune-up is effective at increasing fuel efficiency? Use the dataset provided. So remember, anytime we are beginning a hypothesis test, we have three questions that we need to answer. And remember, the first two questions we can answer in any order. So we need to know how many samples are we working with and what type of data is provided. Now, as you can see, the data set is not being shown to us. So we have to use context clues in the word problem itself. So notice that the words in the problem are before and after. So that suggests two samples. So again, we're measuring the fuel efficiency in miles per gallon of the car before and after it has a tune-up. So we have two samples. Well, let's think about the highway miles per gallon fuel usage. What kind of data is that? Well, miles is a measure, gallons is a measure. So these are both measures, so that means that we are working with quantitative data. And since we have two samples with quantitative data, we have to ask ourselves, are these means dependent or independent? And the answer is that they're dependent. And the reason is because, let's say there's two completely different vehicles. So imagine in your head a very large SUV and a very tiny smart car, right? So it doesn't make sense to compare the SUV's fuel efficiency after a tune-up to the smart car's fuel efficiency before the tune-up. So in order to control for that discrepancy in fuel usage between different types of vehicles, what we need to do is we need to compare the before and after on the same vehicle. So in other words, if I compare the SUV's fuel usage before the tune-up and after the tune-up, right, then I can see if there has been an improvement. So now we can start looking at the requirements. So the requirements for this type of test with two samples in quantitative data and dependent samples, first, as always, we need to have a sample that is random. Then we require that our samples are independent. Now, I know that we are doing dependent samples, so you might say, wait a minute, how can I have independence when I'm working with dependent samples by definition? Okay, well, that is true, right? We are pairing off our data. However, I need to make sure that the before measurement of, let's say, that smart car doesn't affect the after measurement of the same smart car. So again, those measures, even though they're related or they're being paired with each other, they still need to not affect the measurement of the other. And always, we're sampling without replacement, so we need to make sure our sample is smaller than 5% of the total population, and obviously 30 cars is much less than the total population of cars that exist in the world. And then, of course, also normality, right? We always have to meet this requirement. We have to either be told or know somehow that our population is normally distributed, that we're sampling from a population that is normally distributed, or our sample size must be greater than or equal to 30 to satisfy that central limit theorem requirement. So let's go through this. First of all, random, right? We know that we have randomly selected vehicles. We are being told that. Independence, we're going to have to assume here that my after measurement is not dependent on our before measurement, that they're completely independent and unrelated. And we have a sample size of 30, so we can use the central limit theorem to assume normality. All right, so now we have to move on to our hypothesis statements. We've satisfied our requirements, so now we have to ask ourselves, okay, well, we have two samples with quantitative data and dependent means. Right, so with that information, what is the appropriate hypothesis statements to create? So here are our smorgasbord, our options. Okay, so take a minute, pause the video, and see if you can find or identify the correct null hypothesis if we have two means or two samples with quantitative data and they're dependent. So if you said this one, then you are absolutely correct. So now we know that the null hypothesis is that mu sub d is equal to 0. But at this point, you might be like, well, what is mu sub d? What are we talking about? Well, that d stands for difference, because remember what we want is we want to find the average difference in fuel efficiency before and after the treatment. So what we do, again, is we pair all of our samples and we subtract off the before and after data. So we have to define the difference as either x1 minus x2, meaning that would be the before minus the after fuel efficiency, or the after minus the before. So I am randomly choosing this one, x1 minus x2. So again, that's the before the tune-up fuel usage in miles per gallon minus the after. Okay, so let's think about what this means. If the tune-up is effective, that means that we expect the automobile to consume less fuel per mile, meaning that you can drive farther on the same amount of gas. In other words, the miles you can go per gallon of gas should be better, should be bigger after the tune-up. In other words, we expect the x2, the after value, to be larger than the before value. So we can use this information to help us write our hypothesis statements. And again, we already know that our null hypothesis is mu sub d is equal to 0, right? But if we expect x2 to be larger than x1, and we're defining our difference as x1 minus x2, so we have a smaller number minus a bigger number, then we expect our mean difference to be negative. So that means our alternative hypothesis is that our mean difference is less than 0. And again, that would be an increase in the miles per gallon. So now we're on to step 3, which is actually conducting the test. So recall that whether you are using the critical value method or the p-value method, you have to generate a test statistic and or the p-value. And you can do this either using technology or a by-hand calculation. So if you're going to use technology, you have lots of different options, and when you do that, you get this. Now, if you are a person who likes to recreate the results of these videos on your own, please note that for this particular video, I created a data set, I didn't share it. Okay, so you're not going to be able to recreate this data, this information, this hypothesis test, because I didn't give you the data. If you want that, if you want to be able to recreate this, just ask your instructor, ask me, and I will absolutely provide it for you. But just know for this particular video, this is all behind the scenes. I didn't share the data set or the summary with you. So unfortunately, you're just going to have to trust me that with the data set that I have, this is the result. So remember, if you do a by-hand calculation, you have to compute the test statistic. So for paired or matched pairs, this is your test statistic here. So remember, d bar stands for your sample mean difference, and then this is the standard deviation of that set of values. Okay, and then we would stop there if we're going to use the critical value method, because again, we would compare the test statistic to the critical value and see if it lands inside or outside of the critical region. And then if you want to use the p-value method, then you would have to use a t-table. And again, remember, the t-table is a little bit limiting because it does require you to round to 2 digits. Okay, so let's start with the critical value method. So if you find the critical value, then you want to compare it to the test statistic. So how do we find a critical value? Well, we are given a 5% significance level, and we know we're going to have a left tail test because of that alternative hypothesis that said that mu sub d would be less than 0. That tells us we have a left tail test. And then remember, this pesky t-test asks us for this additional piece of information, which is the degrees of freedom. So we have a sample size of 30. 30 minus 1 is 29. So we have a 29 degrees of freedom. So we can take all of that information and we can put it into a cute little t-calculator, and we come up with this nice little picture here. So my shaded critical region is over here on the left. My critical value is negative 1.7. So recall that if my test statistic lands in the critical region, which is the shaded part to the left there, then I'm going to reject the null. If it lands outside the critical region, then I'm going to retain the null. So again, I'm sorry I'm not providing the data set in this video. I wasn't sure how to do that. So just trust me here that my test statistic is negative 5.45, which is tiny, right? That's very, very, very far from the mean. It would be way over here. It doesn't even fit on the graph. So I just put an arrow here indicating that it would be much farther that way. So it's clearly well within the critical region, so we are going to have to reject the null. So if you want to do the same thing using the p-value method, again, traditionally you would pick one or the other, not do both, but if you wanted to do the p-value method, then we have to compare our p-value to alpha, which is the significance level. And as always, if the p-value is less than alpha, we reject the null. If it's greater than alpha, we retain the null. So we already calculated the p-value. Well, technology did that for us, right? So now all we have to do is compare that p-value to alpha. So this p-value, it means that it's very, very tiny. It's less than 0.0001. It's very, very small. So clearly that is smaller than 0.05. So we can conclude, just as we did with the critical value method, that we must reject the null. So now it's time to make a decision, and as I've already stated in previous slides, that both methods lead us to reject the null. So now we can summarize this by writing a statement. So recall, our statements are very straightforward and formulaic, not an opportunity for creative writing here. So if we reject the null, we say there is sufficient evidence to support the alternative hypothesis at the blank significance level. And if we retain the null, we say there's insufficient evidence to support the alternative hypothesis at the blank percent significance level. So as you know, we have decided to reject the null. So we will use this formulaic sentence to write our statement. So the key here, remember, you can just lift your alternative hypothesis from the question itself and just paste it right there. So we will say there is sufficient evidence to support the claim that the tune-up is effective at increasing fuel efficiency at the 5% significance level. Now, normally I would end the video here, but there's one other point I want to make, and that is the difference between statistical significance and practical significance. So my question is, right, we know that we have to reject the null. We know that this is a statistically significant difference, and we have proven that we are increasing fuel efficiency. But is it of practical significance? So one data point that I didn't show you is that the mean difference, right, the D bar, if you will, right, the sample mean is negative 0.629. Well, what the heck does that mean? That's about half of 1 mile per gallon. In other words, you can go half a mile more for each gallon of gas that you buy, right? That's what we mean. So to determine if this is a practical significance, what you would need to do is you would need to figure out, well, how much money is that saving me over time? And I think we can all agree that a tune-up isn't going to last for the rest of the lifetime of the car, right? Maybe it'll last 6 months, maybe 12 months, right? But it's not going to last forever. So you would want to figure out, well, how much money am I saving by being able to drive a little bit more on the same gallon of gas, right? How much money is it saving me? So I haven't done the math. I don't know. But let's just imagine. Let's just make up some numbers here, okay? Let's say that the tune-up were to cost $500, right? And if the tune-up only resulted in a total savings of $200, right? Have I saved myself any money? No, I absolutely have not, right? I've actually spent $300 and gotten nothing for it. Now, conversely, right? If the tune-up cost $200 and it saved me $500, right? Then we're good, right? That means that I have a savings of $300. Okay, so that's what we mean when we say we need to examine the practical significance, not just the statistical significance, when we do these hypothesis tests. Okay, so now that you've watched this video, you should be able to conduct a two-sample hypothesis test for two dependent means.